Hi, everybody. Welcome back to the Astro Imaging channel. This is Alex, and I'm here with Eric and Terry, and Molly's in charge of the show tonight. And Ellie White's here. She's come all the way from, well, she's actually sitting at home, but she's coming to us from the Green Bank telescope, and she's going to be telling us about the pointing and metrology system, how they measure things there and stuff like that. And she'll be with you in just a couple of minutes or so while I have to do some introduction stuff now. And so I'm going to be presenting my screen. And first thing I want to do is I want to go to the calendar. Ellie's here tonight and Linda's coming. I'm really proud that Linda's going to be here next week because she's one of us. She comes here every Sunday night and she visits with us and contributes to the conversation like I hope you're all going to do tonight. And she took the step of volunteering to present for us next week on Beyond the Hubble Palette, how we can get some data from our narrowband imaging and we turn it into other things, more natural looking images than we sometimes get out of narrowband data. Carrie Ann will be back. She's been here before. She does marvelous work. We got Astro Landscape Planning. That's what she's going to be telling us about next week. We finally got that title all set and straightened out. AstroPixel Processor fans, y'all should know something about this program. It's pretty good. And Brent Maynard's going to tell us about that on September 27th. And Andy's coming up from Australia. Actually, he'll be here on the internet. We didn't fly him up. And he's going to tell us about creating dynamic images, Andy Astro. Then we've got a blank. And then Barbara Harris is going to be telling us about observing variable stars with a DSLR. And Amy Astro will be here. You'll notice that blank. How could you fill that blank? Well, if you've got something to share, I highly encourage you to participate in the Astro Imaging Club. You know, it's not just a channel. It's not a bunch of people sitting in a studio someplace. That's pretty obvious, isn't it? Where they practice things and they produce this big show. No, it's people that like astro imaging that want to tell us astro imaging stories. And if you're one of them, and you wouldn't be watching if you weren't, then you've got something to share with everybody. So please press the contact button, tell us your first name and your last name and your email address, and say, hey, I'd like to present about how I got into astro imaging, some things I've learned in my first year of astro imaging, some things I wish I would have done better in my astro imaging, cheap ways to do astro imaging. There's 1,000 topics out there that I am sure all of you guys can do. So please jump in and be part of this. If you know how to run a PowerPoint or if you know how to run your program pretty good, all you got to do is present it. Those of us who once said, well, I don't know how to work all that Google stuff and I don't know how to do that web stuff. And I don't know. Yeah, right. Since the Kofivis got us, we've been sitting here doing Zooms and webs and Google Meets, and everybody knows how to do it now. So nobody's got any more excuses like that. Also, you'll notice that we're up to 9.43K subscribers, 9,430 some people have signed up to be subscribers. And you too can push this little button and become a subscriber. And we'll send you messages telling you what's happening and stuff like that. But it also helps the program. It means that we're more credible, and YouTube has certain advantages if we can come through with them. So in general, it's a good thing for you to do. Also, over here, this is the meat of what we do here. We ask each other questions, okay? And you contribute to the discussion and things like that. Put your questions in over here. Eric is monitoring them. We've learned to kind of hold off till the end of the presentation to interrupt the presenter, but put your questions in over here and we'll try to get them and we can make a little bit of a conversation of it. Okay, Ellie, get yourself ready. It's time for you to start. So you ready to go? Start sharing your screen and take it.
All right. Well, thank you very much, Alex.
Okay.
I really appreciate it, and I'm really glad to be able to present today. So just going to pull my presentation up here. Let's see. All right. So just to give a little bit of background, first of all, thank you so much for the very kind introduction. I'm actually an undergrad at Marshall University studying physics in my third year now. So I've been doing student research with the Green Bank Observatory for the past 4 years, which has been a great experience. I actually live 4 hours away, but it feels like home most of the time. So yeah, so today I just wanted to give a presentation. It's kind of in two parts. So the first part, I'd like to go over just some kind of general how to deal with atmospheric effects like refraction for general telescope pointing. And then the second half of the presentation, I'd like to focus more on my specific project with the GBT and its pointing system, Green Bank Telescope and its pointing system. So this first presentation, actually, I'm giving partly on behalf of Patrick Wallace, who is the founder of T-Point software. So yeah, so I'm really to get started on that. So yeah, so of course, when we talk about astronomy, imaging, all those things, it's really important to be able to know exactly where you're looking and make sure that you're pointing at the right place. So that's kind of fundamental to everything else. So when you point at an astronomical target, you have to be able to predict what direction you're looking in. So if you start, for example, from a star catalog entry, then there's a whole string of calculations that you need to do depending on the level of accuracy that you are trying to achieve. For example, you need to correct for the precession of the Earth's poles. So, of course, the Earth's axis is slightly tilted. As you probably know, it goes through a rotation every 26,000 years. So you have to correct for that slight motion. You have to correct for the rotation of the Earth. And after you do all those things, you have to correct for refraction. So refraction happens because as light from a target travels through the atmosphere, it encounters air of increasing density and bends as it does so. This makes the target appear higher in the sky than it would if the air weren't there. So you can see this diagram here. If you look straight up towards the zenith, then the bending is actually zero because you're actually piercing perpendicular to the atmosphere. And you can see by Snell's law there, which I've put up, anyone who struggled through high school, college physics knows, has kind of had this beaten into your head. But so what that basically says is if you're pointing directly through perpendicular to kind of the interface between a medium and a thin medium, say the atmosphere being the thick medium and outer space being the thin medium, then there's no bending. But if you point at an angle that is slightly that is not perpendicular to that, to that interface, then you're going to get more bending. So basically what that ends up meaning is that the further you point towards the horizon, the more refraction you're going to have. And basically the further away the image that you see is from the real position of the star, as you say. So, yeah. So for example, at 45 degrees from the zenith, at sea level, the refraction makes the target look an arc minute higher than it actually is. 20 degrees from the horizon, the effect is about 3 arc minutes. So basically that has the effect that when the lower limb of the sun is setting and it touches the horizon, the whole disk actually would have set, in fact, if it weren't for refraction. So now I'd like to see if you can imagine a perfectly equatorially mounted telescope, precisely polar aligned and tracking at exactly 15 arc seconds per sidereal second. That's kind of the standard tracking rate. So if you point at a star high in the sky, then as the star starts to set, sinks lower towards the horizon, it would actually get more and more ahead of the tracking as time went on, because if you remember, the further down you go, the more refraction happens and the star actually kind of starts being refracted up higher. So your telescope tracking would get ahead of your source. So this can be corrected by slowing down the hour angle drive by increasing amounts as you descend. So kind of the neatest way to accomplish this in the control software would be to calculate continuously where you're looking, calculate the corrections all the time, and make drive demands accordingly. In other words, it's better to think of it as constantly changing the direction that you're pointing rather than trying to model like a tracking effect. So one thing that is of note here, and this will be relevant later on as well, Refraction actually doesn't have anything to do with the telescope and mount's pointing model, like you think of a T-point pointing model, for those of you who are familiar with that software, because the pointing model corrects for telescope machinery, and I'm going to be talking in a lot more depth about what that means later on. But basically, the refraction just has to do with kind of the conditions at your observing site. It doesn't have anything to do with your telescope. So yeah, so moving on to the next thing. So more on those conditions. So calculating the refraction to useful accuracies is not too hard. It's pretty remarkable that actually the amount of refraction depends almost entirely on the conditions of the air at the observing site, and not necessarily what happens kind of further up on the way down. Mathematically, this would be exactly true if you were like on a flat Earth, but of course we're not, so it's not completely true, but you can kind of approximate. But although the changing conditions as the light beam travels through the atmosphere do cause disturbances, they do, to a large degree, cancel out. So basically, weather readings at the observatory are pretty much all that you need to get some pretty accurate calculations of how to deal with refraction. The size, the amount of refraction depends on how much light is bent by the air, which depends almost entirely on your pressure at your site. And temperature and relative humidity also play a role. So in addition to this, color matters. And so I'd like to talk a little bit about how each of these factors creates an impact. So because the air pressure at a given site changes by only a few percent, for many users, a fixed refraction correction is good enough. That's all that you need. But for even better results, it's best to take account of weather readings. And this will basically, so for example, consider a star that's 30 degrees above the horizon at a sea level site. Pressure, for example, say your pressure is 1,000 hectopascals or millibars, temperature is 10 degrees Celsius, and humidity is 50%. So take that as your control, and then let's kind of go through an exercise and see how each of those, if you change each of those factors, how much does that change your refraction? So say that your light is green. The amount of refraction that you're starting with is 99.149 arc seconds. So that's a bit over an arc minute. Actually quite a bit over an arc minute. But if you change the pressure by 10 hectopascals, and that moves the star 0.993 arc seconds. So if you change the temperature by 1 degree Celsius, that moves the star 0.357 arc seconds, and so on. If you change the relative humidity from 50% to 100%, the star moves 0.087 arc seconds, which is, you can see that doesn't, you've changed the relative humidity by a whole 50%. That didn't really do much. So if you change the color from green to 400 nanometers, which is more on the blue-violet side of the spectrum, that moves the star by 1.754 arc seconds. So you can see that kind of the most substantial things that can change where your source is going to appear is your pressure and color. So that's kind of an interesting thing to note when you're thinking about what kind of data you might need to take at your site to do these corrections. So let's talk about how we want to determine pressure at our site. Knowing the pressure can be tricky. If you Google, for example, pressure in Albuquerque pressure, it will say something like 29.95 inches of mercury. But that's not the pressure that you want. That's actually what you have to set your altimeter to read 5,355 feet at the airport. So that's the setting you have to set in your airplane to let it know what your altitude is. And this measurement is called QNH, which is in reference to the Q code used to signify atmospheric pressure, adjusted to mean sea level. So this is basically what the pressure that you would measure if you were at sea level. So what you really want is your pressure with respect to where you actually are, your actual elevation. So for that reading, you need to take you would want to take a measurement called QFE, which is also another Q code used by pilots. And if you figured out what this, what this pressure is, in Albuquerque, that would be 24.5 inches versus the 29.95 inches measured with respect to sea level. Basically, the bottom line of all that is if you want to determine your pressure at your telescope site, you want to be measuring it from ground level where you are, not sea level. So you need your QFE reading, not your QNH reading. And one quick kind of item of note, these Q codes, you can remember them by query field elevation, that's the kind that you want, or query nautical height, which is the kind that you don't want for telescope corrections. So that's just kind of an important distinction there. So moving on, I just wanted to talk a little bit more about some other effects that you can see that need to be corrected for. So a telescope control system that corrects changing air conditions continuously is likely to introduce tracking jitter because of the noise in the readings. It's safer to take the readings at the start of the exposure and leave them fixed. Alternatively, you can kind of average out kind of some of these effects over a longer period and make less frequent corrections, so that you aren't constantly updating your mount and causing it to shake. So because refraction depends on zenith angle, so the angle again from straight up, a star field will appear squashed vertically. So if you think about, pointing slightly down from the zenith, your source is going to be refracted slightly up. If you look slightly further down, it's going to be refracted even more up, so it'll be squashed in the vertical direction. So this effect or distortion that's caused by this is called differential refraction. Kind of the formal definition is the change of the apparent place of one object relative to a second object near it due to atmospheric refraction. And you don't want to confuse this with atmospheric dispersion. Sometimes people do confuse that, but that's another thing entirely, and I'll talk about that here in a minute. So differential refraction is therefore an important effect to consider when predicting what pixel the image of a guide star should land on. So I've included this image here because I think it's a really good illustration of it. So you can see as the sun is setting, its shape is actually changing. So it's becoming squashed. So this is basically a really good example of differential refraction. Because even at that, even though the sun kind of spans that small angular distance on the sky, the difference between the top of the sun and the bottom of the sun in terms of the refraction index or the refraction amount causes it to squash. So that's kind of an interesting representation of that. And the same thing happens with the stars. They just become closer together. In addition, so how do we kind of correct our polar alignment to account for refraction? So as an equatorial mount tracks a field, because the amount and orientation of the vertical squash due to differential refraction is changing, stars in different parts of the field will trail by different amounts. This can in principle be reduced by deliberately changing the polar axis alignment to match the field that's being observed, so actually moving the polar axis during an observation. There's at least one telescope that does this, the UK Schmidt 1.2 meter optical telescope in New South Wales, Australia, picture on the left there. It has a motorized jacking system to do exactly that, to update continuously to correct for refraction. But for most users, that's not necessarily practical. So the best compromise is to set your polar axis to the refracted pole rather than kind of your non-refracted pole, which is what you would get using, so the no-air pole is roughly what you would get doing the drift method of polar alignment, but you need to use a slightly more complex method to correct for refraction. And basically what that would consist of is setting your alignment to a star, which you would determine from your site to fall at the pole, accounting for refraction. So that's a bit more complicated, but there's a lot of kind of really good resources out there to kind of tell you how to do that. Pretty cool. And again, it does depend, all of this depends on what degree of accuracy you need for your observing. Yeah. So just one last thing that I'd like to talk about with this part of the presentation is atmospheric dispersion, which I mentioned briefly before. And this is the color effect of refraction. So we talked a little bit ago about comparing, like, if you looked at a source that was green versus if you looked at a source that was more blue-violet, they would be like an arc second, almost 2 arc seconds apart. So you can see the effect of that in this image of Saturn here on the bottom kind of right area. You can see how it looks kind of spectrum-y. It doesn't look like a normal picture of Saturn. It looks like the colors are all kind of spread out. So basically what this means is the blue parts of a star in an image will seem slightly higher in the sky than the red parts. This is because the wavelength of light kind of determines how much it's refracted by, or the frequency. So this is, so this is really kind of a pain when you're trying to look at planets and they're low in the sky. So if you don't want them to appear like this weird way, if you want them to look like they're supposed to look, then you would need to correct for this atmospheric dispersion effect using an atmospheric dispersion compensator, or an ADC, which is just an arrangement of prisms that intercept the light before it kind of reaches your imager or your eye. And it basically just kind of refracts those separate colors back into an image so that it looks clean, like this image here on the bottom right of Saturn that's been corrected. So a quick example would be if you're 25 degrees above the horizon, the violet part of the image would be, again, about 2 arc seconds higher than the green part, which I mentioned before. So so that's kind of that's kind of, just to sum up, things that you need to think about are atmospheric dispersion, differential refraction, just kind of wholesale refraction, your pressure, humidity, temperature on site. So these are all things to think about when you want to correct for the atmosphere's effects on your observing. So with that, I think that would be a good time to move on to the next part of the presentation, which is I'm pretty excited about. So is everybody there doing okay?
Yeah, we can see you.
Okay,
go ahead. We're now seeing the Great Bank Telescope.
All
Did
right.
we ask questions from the first half of the presentation before she transitions to this next half?
Yeah, that would be fine.
Yeah, I have a few questions, mostly notes. So when you're building a model, whatever modeling you're using, doesn't that correct for a lot of those atmospheric effects that you were talking about? And do you have to somehow correct for it separately, other than just building your model? When your model tracks across the sky, so it should take care of most of those things, right?
Right. So so when you think about like a pointing model, so the refraction model and kind of the more general pointing model are kind of like two separate things. But if you have like a refraction model based on your measurements of humidity, temperature, and pressure on the site, then you can kind of use that to correct in your by setting up your software or whatever you're using. But the pointing model itself deals with a kind of a completely different set of things. So actually you would want to correct your pointing, basically your catalog coordinates for refraction before you would give them to your pointing model to work on. So the pointing model corrects for kind of telescope dependent effects, depending on your machinery and things like that, which I'll talk more about the details of what kind of errors you might need to correct for with a pointing model. But hopefully that answers the question. If not, let me know.
Well, a couple more quick questions.
Sure.
A few arc seconds is likely not important for us imagers.
Yeah.
In fact, with all the disturbance in the atmosphere, probably the variation's a lot more than that. I mean, we should be so lucky to be down to a few arc seconds.
Yeah. Yeah.
So that's kind of a comment. And what elevation does atmospheric dispersion really kick in? Would you say, or important enough let's say Saturn or Jupiter or Mars?
Yeah, so that's a really good question. So I think it's definitely worse, of course, at the lower elevations. But yeah, so the example that we looked at was 25 and 30 degrees. So that was like the 2 arcsecond values. So I'm actually not sure what would be like the maximum like kind of error that you would see there, or the minimum. But yeah, but I can try and look that up and get back to you on that if that would be helpful.
Well, it just came up. Alex, do you have any more questions?
Yeah, I did want to ask something.
Sure.
Obviously, we always want to do things as precisely as we can, but to put it in perspective, our fields of view are anywhere from 3/4 of a degree, 3/4 of a degree to a couple of degrees by a couple of degrees. And if we are measuring things as to their position, we probably tend to measure them compared to other objects in the field, other stars in the field. What is your Why do you need to be so precise about your measurement?
So that's a really good question. And so I can definitely answer this in the context of radio astronomy. And I'm actually going to go into a little bit more detail about that here shortly, about why every last arc second counts. But for optical imaging, I'm not quite as familiar, to be honest. All of my research has been on radio astronomy, but I would imagine that in terms of like if you want to get like really precise with your tracking and avoid any kind of like smearing or anything like that with some of your bigger telescopes, that's where kind of the precision becomes important. But with radio astronomy, it's actually it's vital to have accuracy within an arc second or two, or even a fraction of an arc second. Because of the way that the receivers work. But again, I can get into that in a little bit more detail with kind of some pictures too, if that sounds good.
Well, probably for us, we're diffraction limited long before we reach anything like an arc second. At least I am.
Yeah, so that's another thing that is probably something to take into account, is the fact that that the atmosphere is transparent to radio waves. So I think, so in a lot of cases, like especially at your lower frequencies, you can be observing on a completely cloudy day, rainy day, terrible weather. You can still observe with a radio telescope. So yeah, so that I think could be a factor as well in terms of we're not limited as much in some of those areas in terms of kind of seeing and stuff like that.
Okay, thank you.
Oh, thank you. Yeah, so I guess I'll go ahead and kind of get started on the second half of the presentation, which I'm pretty excited about. So, so this is a project that I've been working on for the past 3 years, kind of trying to analyze the pointing performance of the Green Bank telescope. So worked, of course, on it with a bunch of other people who I've listed here. It's been a really interesting project. So I want to tell you a little bit about it. So first, I know a lot of people here are kind of on the optical side of things. So I thought I'd just give a brief introduction to multi-wavelength astronomy and why I think it's really cool. So I really like this image because it kind of gives a perspective on how how we can see out into our universe from the planet Earth. So this kind of shows, of course, the electromagnetic spectrum ranging on the long wavelength end. You have radio all the way up to your really short wavelength end or high frequency range of gamma rays. And so if you notice this image, you can see these kind of waves here kind of show how far into the atmosphere you have to go to be able to see in these wavelength ranges. So for example, you can see radio, the waves go all the way to the ground. That means that you can see radio waves easily from the ground. the atmosphere is transparent to radio waves. Whereas if you look at the higher frequency end of radio waves and the lower frequency end of infrared, as well as pretty much all of ultraviolet, X-ray, and gamma ray, you have to, you have to actually go up either on a plane or a balloon or in a lot of cases into outer space to be able to do any observing. Of course, optical astronomy, we all know you can do that from the ground. So yeah, so that's kind of, I just think that's kind of a neat representation of why we have to do astronomy the way that we do it, what we can build on the ground versus what we need to launch into space. So, so multi-wavelength astronomy, though, what does that really mean, and what does it give us? So if you want to really fully understand an astronomical source, it's really important to have a complete picture of it. So you want to look at as many different wavelength ranges as you can. So this image here, these are all pictures of the same object, the Crab Nebula. But you can see that each one is vastly different from the other. So for example, if you look at the X-ray image, you can see actually there's a pulsar inside the Crab Nebula. You can see what it looks like. But whereas if you look at NRAO, the radio image from the National Radio Astronomy Observatory, you can see this really interesting structure. The visible light image, very familiar to all of us, I think, shows kind of the nebula structure. So you can see all these different really fascinating things just by looking at just by using different kinds of telescopes. So I spent most of my time focusing on radio. So that's what I wanted to talk about today. Of course, the Green Bank telescope is a radio telescope. So that's what we're going to be talking about, focusing in on. So just to give kind of a brief overview of why radio waves are cool, why I think radio waves are cool for astronomy. For one thing, they let you see through dust. So if you look at something, so that's something you can't necessarily do with optical astronomy or even infrared astronomy. But radio waves can actually penetrate dust, so you can see things in the universe that were previously hidden. So you can look at radio waves are also really good for looking at cold objects. They're lower energy than, say, optical waves, or of course, obviously gamma rays. So you can look at kind of lower energy, colder objects, cold gas. So in addition, radio waves let us find lots of really fascinating atoms and molecules in space. So for those of you who kind of follow space news, you may have heard a couple of years ago, the GBT detected the molecule benzonitrile, which is really fascinating in terms of its implications for prebiotic chemistry in space. Of course, it's discovered lots more molecules since then. It does some really fascinating research there that I think is really amazing for thinking about, if you think about it in the context of, could there be life out there in the universe? Radio waves also let us study these really exotic objects like pulsars, of course, which are, of course, the dead remnants of stars. They also let us kind of discover these really weird, cool objects called fast radio bursts, which we still don't know exactly what they are. Some people have said, maybe they're aliens, and, you can't completely rule that out, but I think it's becoming more and more likely that they are coming from some sort of kind of natural source, like a magnetar, which is a highly magnetized pulsar or something like that. So anyway, in any case, it's still a mystery. Exciting to see where that goes next. So they help us learn about things like supernovae, explosions in space, active galactic nuclei, quasars, and so on. So that's pretty interesting. And finally, my favorite, radio waves let us look for ET. Of course, these days, SETI, or the Search for Extraterrestrial Intelligence, encompasses, is also becoming multi-wavelength. So optical observatories are getting involved as well as many other types of observatories. But radio astronomy is kind of where SETI got started. In Green Bank in 1960, actually, was the first SETI search ever done. So that's kind of why I think that radio waves are really useful tools for radio astronomy, for astronomy in general, and why radio astronomy is such a cool field. So I want to talk now about the Green Bank telescope, which is, of course, the world's largest fully steerable telescope of any kind. It's a radio telescope. And because of that, it's actually surrounded by the National Radio Quiet Zone, which was established in the 50s to protect Green Bank as well as a nearby military facility. And basically, it regulates any transmitters or anything that gets put up in the area. So the telescope is, of course, giant. It's 100 meters by 110 meter dish, weighs 17 million pounds, and operates over an incredibly broad range of wavelengths from 0.3 to 115 gigahertz. So it's actually 20 years old this year. It was dedicated in the year 2000. So yeah, so that's kind of the telescope that we're going to be looking at in terms of pointing. So this telescope, I kind of briefly went over some things that radio astronomy can do. Pretty much anything that you can think of, any astronomy news story or anything, almost anything that you can think of, GBT has been involved in some way. So it performs research on everything from cosmology to fundamental physics to dark matter and everything in between. So one thing that you might notice about the GBT is it's funny looking. It looks lopsided. So a lot of radio telescopes, if you think about like the Very Large Array in New Mexico, which was in the movie Contact, the dishes have their kind of boxy structure here, which we call the feed structure. It's centered over the middle of the dish. But for the GBT, it's set off to the side. And this is actually a really advantageous design because it, for one thing, you don't have a box right in the middle of the dish blocking the radio waves from coming in. For another thing, you don't have like metal structures that go up in the middle of the dish, and that can cause interference to bounce back into your dish, and you don't want that. So the offset arm really kind of mitigates a lot of that, a lot of those problems. But it creates some problems on its own. It creates a very lopsided structure, which can be difficult to deal with. And that makes the challenge of pointing the telescope even more challenging than it already is to point a 17 million pound piece of metal. So needless to say, we need to apply a pointing model to be able to point accurately enough to do this really incredible research. So there are a lot of things that can affect how a telescope points. So we talked earlier about things like refraction and precession and accounting for the Earth's rotation. Well, the other part of that that is completely dependent on your telescope. So a pointing model basically corrects for everything to do with your telescope that's specific to your telescope and its design and structure. So one thing that you have to be mindful of is gravity. Gravity can have an impact on your pointing direction. It can cause this structure here, which is again called the feed arm. It can cause it to bend, which changes the direction that you're pointing. Gravity, of course, can deform the rest of the structure as well. Any kind of deformation can cause pointing deflections. I mentioned here we have to account for geometry. Basically, what that means is your axes, your azimuth and elevation axes, could be slightly different from perpendicular. You want them to be perfectly perpendicular to point correctly. If they're not, you have to correct for that. Of course, you have to be mindful of temperature and weather, and not just for refraction. Temperature can cause your telescope to flex and bend. It can cause, basically, it can cause all the metal to expand. If you have one part of the telescope that's heated up, that part will expand. If one part is cooler, it will be more contracted. So you have to be mindful of that because that can change your pointing direction as well. Finally, another important thing to take into consideration is the track. So if you look at the bottom of this image, you can see that the telescope is resting on a concrete track and it's actually supported, the telescope itself is supported by 16 wheels, so more than 1 million pounds on each wheel. So you have to correct for any kind of tilt of the track and also any bumps in the track, which can cause your pointing to deflect slightly. So we've talked a little bit about pointing in general, but why is it important? Like everyone was saying at the break, for a lot of purposes, especially like kind of astroimaging, things like that, it may not matter so much, but for the GBT, it's vital. So So the Green Bank telescope is expanding its reach into ever higher frequency observing. It goes up to 115, 116 gigahertz right now. The dream would be to go up even higher in the future. But at that point, pointing accuracy becomes really important because the telescope's beam width becomes smaller. So what does that mean? Well, a radio telescope, if you point it at the sky, in most cases, especially for older designs, you'll just be looking at one pixel on the sky. And that pixel's size is determined by the frequency. So if your frequency is really high, the size of your beam or your pixel is smaller. So for example, at the GBT's maximum frequency, 115 gigahertz, the beam size is 9 arc seconds. So if you want to be like reasonably accurately on your source, you really need to have accuracy within 1 or 2 arc seconds for that to be effective enough. So inaccurate pointing can lead to reduced aperture efficiency. Basically just means it can introduce uncertainty into calibrations of your observations. And all what this means is you could be looking at a source and you might think it's a certain brightness, but you might be off center or you might be slightly off in some way. And so your mere measurement is not going to be as accurate as it needs to be. So that's kind of why it's important. And I'd like to go a little bit into the nitty-gritty of how it works. So there's a lot of components to GBT pointing corrections in addition to just the model that corrects for the pointing effects. So of course, the pointing model itself is basically a set of equations that relates the telescope's encoder coordinates, which are kind of what you would read if you actually went over to the base of the GBT and looked at if there were a dial, which there isn't because it's digital, but if there were a dial, that's what it would say where it would say it was pointing. So you want to relate those encoder coordinates to the observed place of the celestial object. Now, what is the observed place? Well, the observed place is basically catalog coordinates corrected for effects like refraction and precession and all the things that we talked about before. So the pointing model basically takes, creates these corrections that you need to add into the observed coordinates to get to the encoder coordinates. So in addition to the pointing model, you need a tracking model. This also corrects for translations of the subreflector. So what is a subreflector? Well, let's look at the telescope here. If your light comes in, bounces off the main dish, you can see there's a little dish here. And the radio waves bounce off and into this little cabin here. This is called the receiver cabin. And that is where the equivalent of your cameras are. They're called, for radio telescopes, they're called receivers. And they collect the radio waves and then send it back to the electronics in the lab. So you need to correct for any kind of movements that go on with this subreflector, because that can create errors as well. So in addition, you need to make sure that you're correctly correcting for any kind of errors with the dish. So the dish actually can deform when it moves. It actually has an active surface, which serves to smooth out the dish, which is especially important at higher frequencies. So that's also something that needs to be accounted for. And finally, last but not least, another thing that has to be accounted for are local pointing corrections, which are per session calibrations that observers have to do before they start. And I'll talk about those in more detail here soon. Okay, so how do we get the data that we need into the pointing model? Well, we talked about in the first part of my presentation, I mentioned, apologize for that. I think a cat is acting up in the background. So talked about in my last presentation about how, about how you want to have a weather station set up so that you can measure things like temperature and humidity and things like that. So the GBT has a suite of systems that measure important things, and we call those metrology systems. They do measurements. So one of the most important systems that we have is a temperature sensor system. So 19 of the temperature sensors are installed on the GBT, are used for pointing corrections. And you can see in this image, I've kind of noted where each of them are. So the sensors collect temperature data during observations, and the GBT control software then uses them to apply real-time thermal corrections to the telescope. So in addition to that, there are inclinometers installed on a telescope. And what these do is they accurately measure the elevation and cross elevation, which is actually azimuth times cosine of elevation tilt caused by track surface areas. So this basically just tells you, okay, if you're pointing in this direction, there's a bump in the track at this location and you need to correct for it. So we basically take values of the inclinometer's x and y components and tabulate them as a function of azimuth. So let's talk a little bit more about the track corrections. So twice every year, a series of measurements is made by turning the GBT slowly in azimuth and then recording inclinometer readings for the entire rotation. And these measurements are recorded in lookup tables. So later on, when we go to observe, the data in lookup tables is used to apply real-time corrections for track irregularities. So we can make these adjustments as the telescope is moving. So talk a little bit about how it's implemented. I don't want to go into this in too much detail. It looks like a lot of text, but it's really not too complicated. So basically, what happens is the GBT's antenna control software sends mount coordinates to the encoders. And these include the corrections from the pointing model, from the local calibrations, and depending on which receiver you're using, there are some small corrections that need to be applied. So telescope control software just tells the telescope, okay, this is where the pointing model says you need to go. So now I've mentioned that I'd talk about local pointing corrections a little bit earlier on. So basically, LPCs, which is what they're kind of abbreviated as, are elevation and cross elevation offsets that can be derived by an observer taking a cross scan of a really bright calibrator source at the beginning of an observation. So this just tells you, gives you an idea of how well your model is doing, because sometimes the model won't correct for everything, and you need to do a little bit of cleanup to correct for some offsets, offset errors. So this calibration just takes away any additional kind of errors that remain, hopefully. So a cross scan is basically just a series of forward and backward scans in azimuth and elevation. And yeah, so it just lets you figure out what remaining errors exist that you need to correct for. So basically what I've been working on over the past few years, among other things, has been to work on doing a really thorough analysis of how well the GBT's pointing actually performs. So I'm going to show you a few plots here shortly that I made using the telescope modeling software T-Point. And I ran the analysis in two different ways. One is blind pointing. So what that basically is it's just what would happen if you told the telescope to point somewhere after just applying the pointing model without any corrections, any calibrations. So the other way that I ran the analysis was that I would actually apply an offset at the beginning of each observation, and that would not quite simulate what you would see in a real observing session, but it would give you an idea. If you did one calibration and then did a whole bunch of observations across the sky, how much error would you see? So we did some, and this last bullet just means we did a lot of quality control to make sure that we would reject any kind of bad scans that were corrupted by wind or other kind of effects that have nothing to do with the pointing model. So I'd like to show a couple of plots that I think are really good to explain how these work, how well the telescope's pointing. So this is basically a view of what you would see if you could look through the GBT, which unfortunately you can't, but if you could, this is kind of how the errors would be distributed across the field of view. So you can see actually with just the pointing model applied, no calibrations, your standard error would be about 9 arc seconds. And that's really, really good. So we're really pleased with that. You can do observing at a lot of frequencies where that's sufficient, and you wouldn't even need to do a calibration at the beginning at really low frequencies, like L-band, for example, which is where the hydrogen line is. So the plot on the right here shows that if you do one calibration at the beginning of an observing run and then do take point sources across the entire sky, you would see about 5 arcsecond error. So these are both really, really exciting results. Show just how well we're able to point the GBT despite its tremendous size, and just kind of it seems very cumbersome, but it's actually quite good at getting these really accurate values. And it gets even better than this. So you may remember close to the beginning of the presentation, I said, you know, the GBT, we need to be able to point within 1 or 2 arcseconds to observe well at 115 gigahertz. Well, actually, one of my co-authors, Dave Freyer, recently did an analysis, and we found out that if an observer does a calibration within 10 degrees of their target source, and then they do that observation within an hour of that initial calibration, the accuracy is about 1.2, between 1 and 2 arcseconds, which is exactly as it should be. So that's kind of more representative of how an actual session would go. You would be more likely to do a calibration close to your target source and within kind of this a very close time period. So that's a really, really promising result, as are all of these. So just to show a couple more, these are just basically pointing error versus time. So you can see that they really, there's really not a bunch of time degradation in other words, the pointing model doesn't get a lot worse as time goes on. So you can see a little bit of kind of error, maybe some structure, especially on the left, which could be due to seasonal variation. But in general, it looks pretty good. These plots look even better. This is a plot of pointing error versus azimuth. So basically, this just looks like completely random noise, and that is very promising because it means that there are no unaccounted for azimuth-dependent effects that we haven't modeled out. So finally, last plots I'd like to show you. These are pointing error versus elevation. Again, looks pretty much like noise. That's a very good thing. So yeah, so basically, so that's kind of where we're at the moment. But of course, there's more to do. So the GBT's current pointing performance, as we've seen, is excellent. But always we can make further improvements, especially as we try and see if we can push the limits of the GBT's capabilities. So here's just kind of a list of things we could do. We could work on kind of adding, subtracting terms to the model, see if we can improve the accuracy more. There's things we can do. I think maybe including more temperature terms in the model could lead to improvement, but we'll see. We could investigate ways to more fully implement wind corrections from the quadrant detector, which is an instrument on the telescope for general observing. So this method currently shows promise for observers who are using the Mustang receiver, which is used a lot to look at star formation and various things. So it'd be interesting to investigate that. Another thing we could look at is incorporating anomalous refraction into the pointing corrections pipeline. Now, anomalous refraction is just, we didn't talk about it in the earlier presentation, but it's basically a little bit more local refraction effects that a lot of observatories correct for that could lead to some improvement. So another thing that we could try is looking at better quantifying some track errors and how they propagate into the rest of the system. And of course, there's probably a lot of ideas that we have not even thought of yet. So that's always an exciting thing to think about. So just to wrap up, in conclusion, the GBT is faced with some unusual challenges in achieving optimum pointing due to its very unusual design, but it achieves really excellent performance anyway. So incorporating metrology data, another thing we've seen, the temperature sensors and inclinometer data allow us to correct for environmental effects in real time. So we've also seen that calibration measurements are important for achieving optimum performance at the highest frequencies. Even though we do get really good blind pointing, it would still be ideal to be able to improve that performance as well. Because the better your blind pointing is, the fewer calibrations you need. And if you have to do fewer calibrations, observers have more time left to do their science, which is always a good thing. So just one final note of thanks. Thanks to funding from NASA West Virginia Space Grant Consortium, I'll be working with mentors at the Green Bank Observatory to continue research into GBT pointing and metrology systems during the 2020-2021 academic year. Yeah, so finally, just a big thanks to first of all, I'd like to say a big thanks to Dr. Richard Prestige, who was mentioned on the co-authors list. He was my mentor for several years. Unfortunately, he passed away last year, but he was a major contributor on this project and just a wonderful mentor. So a big thank you to him. Of course, all my mentors, co-authors, Green Bank Observatory staff, Marshall University Physics Department, West Virginia NASA Space Grant Consortium for their generous support, and of course my family for their support as well. So with that, I am happy to answer any questions that you might have.
Well, we have a few comment questions, if you can kind of bear with us. Some are simpler than others.
Sure.
So you mentioned in the beginning, you're looking through dust, and I'm sure everyone understands you're looking through the dust and DSOs in the universe, not dust in the atmosphere.
Right.
I'm sure everyone understands that, but I just made a note. And you can run day or night, right? I mean, it makes no difference, right?
Right. Yeah, something that maybe I should have qualified. The data that that I was showing you was all taken during the night. So for higher frequency observing, nighttime is preferred because of the temperature stability. But you can observe at any time of day, especially for your lower frequency receivers. So it really does depend. The telescope is one thing that's really amazing about it is it covers this range from 300 megahertz to 115 gigahertz, which is really amazing. But that means that there's a really broad range of acceptable operating conditions because at your lowest frequency ranges, you can get by with really, really bad weather conditions and things like that. But once you get up to the higher frequencies, even just like 10 gigahertz or more, then it becomes more difficult in terms of trying to plan your observation to match the best with the weather. And the DBT actually has a system called the dynamic scheduling system, which is common to a lot of observatories nowadays, which basically means observers can put in a proposal, and if they need to use the higher frequency receivers, they'll get priority on really, really good weather days, and people who are using lower frequency receivers will get put in whatever, like maybe more inclement conditions.
So what percentage of the sky, the northern hemisphere, can you observe?
Oh, that's a good question. I believe it's 85%. I'd have to check my numbers on that, but I'm pretty sure that's true.
A personal question, you're a junior undergraduate, right?
Yep.
How many publications have you put your name on?
Well, I guess it depends on what kind you mean in terms of like conference proceedings and things like that. Maybe about 5 or so. But in terms of, I'm working currently with all of my tremendous like mentors and co-authors right now on a paper that we're hoping to submit to like Astronomy and Astrophysics or a similar journal, and hoping to get that through. Pretty exciting.
There have been a couple questions about plate solving. We're so used to plate solving an image, but there's really no equivalent to plate solving with a radio telescope, right? You don't take an image and then figure out where you are. Your model instructs you where you are, right?
Yeah, so I guess in a way, kind of the cross scans I mentioned, the calibration scans are a little bit analogous because they let you kind of see how far off you are and then correct. But it is pretty different.
When you do your modeling, do you have criteria for outliers?
Yeah, so that's a really good question. So when I went through and did all the processing, so I basically so to do this modeling and to get these numbers, I basically had to go back through the archive data and pull up like old data sets and run them through pre-processing programs. So part of what I did for that was I wrote part of a program, modified a program that another person at the observatory had written to basically run it through a set of heuristics, which basically what I did was, if you think about looking at a source with a radio telescope, you scan over that source, and if it's a point source, I mentioned this to you guys beforehand, but it looks like a Gaussian. So depending on how well, if the weather is really, really bad, it won't look like a Gaussian. It will look like a really squiggly, weird shape that won't match up with the measurements of a normal Gaussian. So basically what I did with the pre-processing was to write a program to compare the characteristics of the actual scan with how a Gaussian of that scan should look. And if it looked too different, then the scan would be rejected. And in that case, the data would not be included in the modeling and just thrown out.
So another question, someone asked about setting up a neural net approach, or I guess AI, rather than these analytical analysis and measurements of your model.
Yeah, so that's an excellent question, and one that I actually hadn't thought of. I guess just thinking about it a little bit, one thing that comes to mind is it's difficult to get a large enough data set because these models require you to actually take up a fairly decent amount of telescope time to do a pointing run, which is basically just using the telescope, pointing at a whole bunch of sources. This can take several hours, and you have to put in a request and all those things. But yeah, I don't know. I honestly don't know a ton about machine learning, AI, that kind of stuff. I'm really fascinated with learning more. So yeah, thank you for the suggestion. That's really cool to look into.
Not my suggestion. A couple questions just came in. Do you actually get to drive the telescope?
I have a few times.
You sit at the wheel.
Yeah. So it's a really cool thing. If you can go up. So here's a kind of a shameless plug. So every year, at least in normal years, they have a Family Science Day, which you can actually go and take a tour of the facility. You can go up in the control room, learn all about it. So if you're interested in seeing where the telescope is driven from, and you're within like a reasonable distance of the observatory in September of most years, not this year, unfortunately, but then definitely do that. But me personally, in terms of have I driven the telescope? Yes. Actually, last year, just a quick story. I was lucky enough to be in Green Bank at the same time as a group of scientists doing SETI research, search for extraterrestrial intelligence research, were in Green Bank. And so they were kind enough to let me kind of come up with them and sit and watch them do their observing. So that was pretty amazing.
Did they wear tinfoil hats?
That's a good question, but no, they didn't.
I'm sorry. If you look at a model and you see outliers, can you kind of determine where they come from, whether it's one axis or another, whether it's the track, whether it's the elevation?
Yeah, so that's a good question too. So if you look at the data before the model is applied, a lot of times you can see like actually sinusoidal effects. So you can see, for example, if you have a tilt in your track, you'll see an azimuth dependent sinusoid look. So it will go down and then it will go kind of up and back again. And that kind of tells you if you see kind of that kind of signature curve in the azimuth direction, where your pointing errors are worse in certain azimuths and better in others, and you can tell there's a tilt in the track. I think a similar thing works for other kinds of errors. You just have to kind of know what to look for. But yeah, that's a good question.
I think I've run out of questions. Alex, you want to?
I've got one. I've got
Yeah.
one, Ellie. Does stuff in orbit have any effect? Any of the space stuff?
Yes. Yeah. So so that's kind of the bane of radio astronomers' existence is bright satellites. So yeah, so that's one thing that you have to be really careful of is at certain frequencies, there's so many satellites and things that it's almost that it becomes difficult. You have to be really careful about excising radio frequency interference from the data. So it's a lot of times. So, for example, like the Starlink satellites that, as I know, is causing trouble for optical astronomers. It's going to also cause trouble for radio astronomers because it emits kind of in a K-band frequency, which is where a lot of research is done in star formation and other things like that. So satellites can create a lot of problems for radio astronomy.
So do you have to maintain a database to identify potential conflicts and then adjust your schedules?
Yeah, so that's also a good question. So I think it kind of depends. Yeah, I think that is a really good question, one that I don't completely know the answer to, but I do know that we have to be really careful about, like, for example, with the SETI research, you have to know what frequency satellite occurs at so that you can rule out, like, you don't want to accidentally say, oh, I think I found ET and it's actually a satellite. So yeah, so I guess partial answer to your question is there's a lot of documentation about the frequency that each satellite emits at, and that's taken into account when you're looking at your data and determining what frequencies to excise or remove from your spectra.
Thank you.
Thanks.
I have a question. I have a couple of questions. One is you refer to running a T-point model. Is that the same T-point that we use software BISC's T-point, or do you have your?
Yes. So that's
Yes.
a question. So I think it might be slightly different. I'd have to look at the different kind of packages and see. I think it might be. I think there's kind of like a more kind of hobbyist type of T-point, and then there's more of like the larger ground-based telescope T-point. But yeah, I'd have to look into that a little bit and see which package we're using. But I think it's the I think there's two, and we're using the other one.
The other questions may be easier, maybe harder, but earlier in the presentation you showed us a picture, a radio picture. Actually, you showed us in various band passes. The M1, the Crab Nebula. Okay, and it was obviously the Crab Nebula, no matter which. And in radio, it was more than 1 pixel. Later on, you said that you get 1 pixel.
Right.
So am I to believe that this great big old telescope is pointed up there and it's getting 1 pixel?
Right. So that's a really good question. And the answer is, in a lot of cases, yes, especially for the older receivers. But so basically how you get an image like that, and that one, I don't know what telescope made that image. It just said NREO, so it could have been a lot of telescopes. But if you do use have only one pixel, which is the case a lot of the times, then you would just make a map and just go like sit on one point for a second or however long you need to get enough light in, and then move to the next step, then move to the next step, then and on until you have basically a mosaic. But one really exciting thing with kind of modern receiver technology is there's a lot of kind of multi-pixel receivers being developed. I think Parkes in Australia has had one for a really long time, but the GBT also has a one called Argus, which is a 16-element receiver that actually operates at the very highest frequencies. So that gives you actually 16 pixels on the sky. There's plans, and fingers crossed, hopefully will be developed 144 pixel receiver in the near future. So yeah, so there's also a fairly new design called a phased array feed, which lets you basically get a much broader field of view as well. So there's a lot of exciting new developments going on kind of in that field.
So if you were using a high frequency radio and you wanted to get a picture of the Crab Nebula, you'd have to take a picture for 10, 15, 20 seconds, however long, and then move it 1 pixel, one, arc second or 10 arc seconds or whatever.
Yep.
Take another one, I take another one, I take another one. That's where the pointing comes in, eh?
Yep. Yeah. And one thing that I did want to mention, so probably the kind of radio telescope that a lot of people are more familiar with is the array kind of radio telescope. So again, if you watch the movie Contact, it's the very large array. There's lots of smaller radio telescopes working together. The GBT is a single dish telescope, though it can work as part of an array called the Very Long Baseline Array. But in most cases, it works on its own. So there is a difference there in terms of if you are using an array, you can create kind of a mosaic image using just one pointing or one kind of so all at the same time instead of having to go on each pixel necessarily differently. So that is a little bit different. It depends on which kind you're talking about, kind of.
So something like the VLA, so each of those dishes is tuned to a different frequency, and that's composited, or each of them tuned to the one and making for a larger dish.
Right. So each of them. So yeah, that's a good question. So in a lot of cases, so in the simplest case, they would all be tuned to the same frequency and kind of looking kind of in the same direction, kind of, and then the outputs would be combined to create that that map or that image. But you can have cases where if you have kind of multiple observers using an array at the same time, sometimes there will be different systems so that you can be having some of your dishes operating on this frequency and some of your dishes operating on this frequency. They can even be pointing at a common source. I worked on a project this summer. I worked for Berkeley SETI Research Center. I worked on a project relating to the Allen Telescope Array, which is out in, of course, Northern California. And so basically what you can do with that array is, you can do that exact thing. They have, ultimately they'll have like 4 different frequency settings, and you could even have like 4 subsets of the same array looking at completely different frequencies and at different sources. So there's a lot of interesting things we can do with that.
One question came in a little late. Do any of the satellite companies cooperate with places like Green Bank? So say, we're going to put up the satellite, and we're going to broadcast across this frequency, just be aware.
Yeah, so that's a good question. I don't know that that's the case. I would have to do a little bit more research on that to know if there's actually any kind of feedback that goes on. There are certain protected frequencies. So, for example, there's a really useful hydrogen line at 1420 megahertz. Satellites and things like that aren't allowed to transmit on those frequencies because of radio astronomy protections. But in terms of individual satellites, like actually consulting the observatory before they go up, I don't know that that happens, but a slight tangent from that is that that the GBT actually has been used a lot of times to kind of locate NASA satellites that are missing. Like it found, I can't remember the name now, but some solar and lunar kind of satellites that had gone missing. NASA had kind of lost them, but GBT is so sensitive that it was able to pick them up. In addition, the 140 foot, which, as I mentioned before, kind of we went on air, has the largest ball bearing in the world, as far as I know. Actually, for many years, worked as a ground station for the Radio Astron satellite that's operated out of Russia, which was a basically a radio telescope in space that was just a satellite. And so Green Bank kind of worked with them to basically establish a really long baseline array. So that's one quick tangent to that tangent is that when you're using an array of multiple telescopes, the further away you can space the elements of that array, the better resolution you get. So you can see much smaller sources, make out much better detail. So I think that the Radio Astron satellite was kind of trying the Earth to space baseline type of thing, because that's obviously really far distance. So that was a pretty cool experiment that went on. Unfortunately, it died last year or within the past couple of years, so that's no longer happening. But it was really interesting to hear about when it was.
sort of like the Event Horizon Telescope, being able to get relative. It doesn't look high resolution, but actually a really high resolution image of that black hole.
Yeah. Yeah, exactly.
More questions are coming in here at the end.
Cool.
That's interesting. If you have an array of telescopes, are they all, if they're synced up, they're all using the same model? Or does, actually, the way you describe it, you would have to model each one because they have
Right.
different characteristics, right?
Right, exactly. So the pointing models depend entirely on each telescope's own idiosyncrasies and kind of weirdness. So they have to be made based on each telescope and their unique kind of structural design.
Alex?
Where's Alex?
Alex, can you hear us? We can't hear you.
He's been abducted by aliens.
Usually Alex does our wrap up. He'll be back in a moment.
Can you hear me now?
Yeah, we hear you now.
Yeah.
Ellie was thinking I was sacrificed.
Put on your tinfoil
No,
hat.
I unmuted my Google Meets button, but I forgot to unmute my microphone button. So I'm back. Okay. Yeah, I hear Molly put a note in to get your last questions in. I don't know that anybody's gotten any in after that, but I think Gary did a good job of covering them all. So I'm going to wrap up pretty quickly here. Ellie, if we needed to get in touch with you to ask you any questions, how would we go about doing that?
Yeah, great. So my email address is elliewhite1420@gmail.com. Feel free to send me a note or, yeah, if you need me to repeat it, let me know. It's ELLIEWHITE 1420@gmail.com.
1420, so great. Love it. Love it.
Yeah, it's not nerdy or anything.
Now, we're proud. We're proud.
Okay. Let's see. Anything else out there? Eric, we got everything?
Yeah, I think we're all set. We had a bunch of questions
Okay.
though. And of course, a big thank you from all the people online and us as well. Great presentation. We were all informed and educated. I now know how a radio telescope works, sort of.
Yeah, I could probably run one now myself. Because I've got a shirt that says, what was it? Yeah, I got a shirt that says I can run it. Okay, enough of that goofing around. We did a lot of goofing around before the show today, guys. And we're going to continue to goof around after we sign off. And if you become a presenter, you too will be invited to get here a half hour early and stay a half hour late. And you can goof around with Tolga and Molly and Terry and Eric. Me, it's not so much fun goofing around, but the rest of those people, they're a lot of fun. Anyway, Linda's going to be here next week to tell us about how to get some natural color out of your narrowband pictures, and that's going to be fun. And then we've got some other shows coming up, but we need more people. So subscribe, donate if you like, but definitely offer your services. And if you've got somebody that that's it's a good presenter, somebody that can talk, and you've seen the show, say, hey, how would you like to be on the Astro Imaging channel? You're a personal friend of Alex, and Alex will get you on the on the Astro Imaging channel. Okay, so if you do that, just get on the website, contact us, and tell us that you've got something that you'd like to say. Okay, has anything come in that we need to talk about, or is it time to go?
Time to go.
Okay, Molly, take it away. You in charge.
Not all.
Good night.
Good night all.
Thank you.